Okay then, welcome back to the week 10 of the problem solving session for the fluid mechanics and for the course fluid mechanics and the application. Okay, and this week we will be dealing with a very important topic, that is in viscid flows and potential flows. Okay, so the very first question that arises in one's mind is like, by its very definition, that is in viscid, uh, which which may seem to some people it's like it may define, or it may sound like it tells that the fluid's viscosity is zero, mu is equal to zero. Okay, but as we all know, that's not a real case. Like, there's no fluid in the entire world whose viscosity is equal to zero. Each and every fluid has a certain viscosity. So there's no fluid in the world which has viscosity equal to zero. So it may seem that since something that is not existing, or that is not real, there's no point of dealing with such kind of theories, right? Such kind of flows. But as we have discussed in our previous week's session, that we were dealing with boundary layer theory, right? And we saw that for flow or flat plate, and given the scenario that the Reynolds number of that flow is very, very high, we observed that the boundary layer thickness is very less, and we saw that the boundary layer by its very nature divides the flow field into two distinct regions, that is the inner region and the outer region, where the inner region is a region which consists of all the rotational nature, viscous nature of the flow field, and the outer region is free of all rotationality and viscosity or viscous effects, not viscosity, viscous effects. And there again we also saw that it's not in the outer region, it's not that the viscosity of the fluid is zero, but it's that the velocity gradients in the outer region are so less that they are not able to manifest the shear stresses because of the presence of the wall in the outer region, right? Because we know that, again I will just like to repeat it again, that shear stress is given by mu del u by del y, where the this is the shear stress at any point in the flow field, right? For if it is at a wall, then it will be at y equal to 0. Say, I'm just giving an example. So if it is at any point in the flow field, then we saw that since mu is non-zero, for tau to be negligibly small, this has to be almost equal to 0, right? And we saw that the velocity gradients at the outer edge of the boundary layer, that is at the outer edge of the boundary layer, it's very less. It's not zero. It's not zero, because we saw that by the definition of boundary layer, by the definition of boundary layer thickness, we saw that it is a point in the flow field where the velocity reaches 0.99 or 99% of the free stream velocity. So it is not exactly you. The point where it is exactly equal to you, there the velocity gradients will be zero. But since we are defining boundary layer in such a way that there exists some velocity gradient at the outer edge of the boundary layer, so there exists a velocity gradient, but this is very, very small. It's almost equal to 0, and that's why shear stresses are also equal to 0, almost equivalent to 0. That's why they are not, because the velocity gradients are so small, the fluid is not able to manifest the effect of the shear stress, or the outer region is not able to feel the presence of the wall, because the shear stresses are not manifested, right? Which are only manifested when there exists some velocity gradient, right? So that's why we see that this is the elegance of the boundary layer theory. Like, though by the first impression it may seem like it's like quite strict and restrictive, that outside the boundary layer there is no viscosity, inside the boundary layer entire viscosity is limited inside the boundary. It's not like that. It's just an elegant way of approaching a physical phenomenon and explain it in a very beautiful way. So that's why the boundary layer theory is very important, because it is by the boundary layer theory only we are able to calculate or validate the presence of drag on the flat plate, or in this case upon this airfoil, right? So now as we can see that for the entirety of the flow field, the entire viscous effects are only limited in a very thin region, given that the Reynolds number is very high. So for the most of the flow field that generates over the flat plate, so like if we discuss in this context, for the case of flow and airfoil, most of the flow field that is above the airfoil lies in the inviscid region, and since the flow in the inviscid regions also govern the flow physics of the airfoil, it is basically, it helps in determining the lift and drag. Drag is determined by the physics in the boundary layer theory, but the lift is also governed by the flow that resides outside the boundary layer. That's why it is very important for us to also have a proper understanding of the flow outside the boundary layer, the inviscid region or the potential flow region that resides outside the boundary layer. And that's why the knowledge or understanding of inviscid flows or the potential flow theory is very important in the case of fluid mechanics, right? And like not only in the case of airfoils, but in most of the cases, like where the Reynolds number is usually very high, and that is actually the case in the case of most of our day-to-day life flows, then the boundary layer that will exist upon this object would be very very thin. If the Reynolds number is high, then most of the flow field or flow physics that lies around the body, which also helps or which also has its effect as a net resultant force on the object or net resultant lift, that is the force on the object, is also because of the flow that resides outside the boundary layer. And that's why having an understanding of how the flow behaves in this inviscid region can also help us to get a very proper understanding of the flow physics for most of our day-to-day life objects. Okay, so that's why the knowledge of potential flow theory and inviscid flows are very important. So again, and also interestingly, since the viscous effects are neglected in the case of potential flow theory, the governing equations are also being modified in that context, right? In the case of viscid flows, in the case of viscous flows, we saw that the flows are governed by the Navier-Stokes equation, and similarly in the case of inviscid flows, since the viscous terms are neglected, we will see that the flow will be governed by the same momentum equations, but there the viscous terms are neglected, and these type of equations where the viscous terms are neglected are known as the Euler's equation. Okay. So this equation is actually the non-dimensional form, that we have non-dimensionalized the governing equation in terms of all with respect to all the scaling terms. So here also, like I just want to again emphasize that here also this term is 0 not because that mu is equal to 0, but it's 0 because since this term represents the reciprocal of the Reynolds number, and since Reynolds number is very high, then this term goes to 0, and that's why this term is neglected in the case of potential flow theory. Okay, and now this equation then, and if this term is neglected, the governing equation is termed as the Euler's equation. Okay, here now if we consider the flow to be steady, the governing equation again simplifies a bit further, where the governing equation takes the form of this, where the pressure is then scaled as half rho v naught square. This is basically as the kinetic energy. Pressure energy is scaled as the kinetic energy. Now you may ask, like, why the kinetic energy? Because as I told, like, pressure is a very funny entity. Like, it does not have a specific scaling term like velocity, viscous, the advective term, or the steady, unsteady term, or even the viscous terms have some specific scaling factors that is uniform throughout the flow field. But pressure is, since it's a very funny entity, it actually scales with the factor that drives the flow. If the flow is governed by viscous effects, the pressure will scale as the viscous term, and if the pressure is scaled by the kinetic energy of the flow field, then it will be scaled as the kinetic energy. And as I told, like in the case of flow flat plate, and similarly in the case of flow airfoil, or for most of the inviscid domains, flow domains, the flow is mainly governed by the kinetic energy. And we can also think in that way, that since the viscous terms itself are neglected, there is no point of scaling pressure with as the with respect to the viscous term, right? That's why the pressure here is scaled as the kinetic energy, and if we implement this scaling factor in this term, then we finally get this form of the Gaulin equation. That is for a steady flow with steady incompressible inviscid flow with a free surface, which is governed by this first order non-linear partial differential equation. Okay. Now again a difficult scenario arises. Why? Because initially we started with the Navier-Stokes equation, which was second order by the virtue of the viscous term. This viscous term, this equation was second order. That's why it had two set of boundary conditions, right? Essentially, that were the no slip boundary conditions and the no penetration boundary condition, right? But now, since the equation has become singularly perturbed, right? As I mentioned about singular perturbation and regular perturbation in the case in the previous session, singularly perturbed in the case that the equation nature of the equation have changed after the modification. Like initially, we started with the second order partial differential equation. Now we are having to deal with a first order non-linear partial differential equation. Let me just write it for reference. Right? It's important. First order non-linear PDE. Okay. So since spelling is wrong, I'm sorry. And since the order of equation has changed, now the equation will not be able to suffice both sets of boundary conditions, right? So now it will only satisfy one set of boundary conditions, and in the context or in this context, it will satisfy only the no penetration boundary condition. That is, the velocity normal to perpendicular to the walls are 0. There is no flow through the wall. That the walls are not porous. Like if the walls are not porous, then there is no flow through the wall. So no penetration boundary condition is satisfied. This is basically V dot n cap at the wall is equal to 0. But the no slip boundary condition is not satisfied or is not considered in the case of inviscid flows, because as the name itself suggests that since the viscous effects are not present, there is no point of considering the flow to stick with the wall, because since the viscous effects are not there, so the fluid molecules will now not stick with the wall, but will now slip over the wall with a certain non-zero velocity. That will basically be the velocity of the incoming flow field, right? So the no slip boundary condition is not satisfied. Okay. So now let's important things. Okay. See, for the sake of saving time and also discussing some problems thoroughly, I have considered that I will not go through each and every explanation very thoroughly. Like it's kind of same only. Like I'm trying to put in my ideas also, but for the sake of saving time, what I will do is that since inviscid flows or potential flow theories have lots of formulas, right? Lots of formulas, functions that we need to remember, and like just so that because we are again using them in our problems, it's good that we recapitulate or look into the formulas once again, so that our memories are fresh. Like for me also, like the memories are fresh, and then we can recollect or remember the formulas much more quicker than if we just randomly start to solve a problem. Right? It's not a good way to start solving a problem. So just for the sake of saving time, I will just look into the problem or look into the basic definitions and basic formulas. Look into the formulas, go through it, discuss each and every term, and then just go after and then just then go and just solve the problems. Okay. And now if you have any doubt or any confusion regarding some definitions or concepts, like if I am not able to clear within this given time frame or within the time of this session, it would be wise that you just go through the video lectures once again. Like Professor Gupta, like there's no one better to explain the concepts in a better way than Professor Gupta himself. So it's better that you go through the lectures once again, get a better idea, then come back to this video, see the problems, and you will be able to the grasp the concept and able to solve the problems yourself. Okay. So given that alignment, it's a very long set of formulas or identities. So it's good that I will just go to the formulas and then just apply them in our problems. Okay. So there are some very important terms in the context of potential flow theory. Okay. See, I will interchangeably use in-viscid flow potential flow theory because they are both exactly the same thing. Okay. So not to get confused with in-viscid flow and potential flow theory, they are exactly the same thing. Okay. So in the context of potential flow theory, there are some new terms or new definitions that comes into picture. Okay. Till now we are not dealing with terms such as vorticity or angular velocity in that frequently. We are not dealing with this term frequently. We might have discussed briefly about this term, but we are not discussing it very frequently in our previous discussions. We are basically dealing with the pressure gradient, velocities, density. We are just dealing with those primary variables. Okay, but now we will dealing with some special variables or parameters. So it's good that we start by defining them. Okay, because this will come very frequently in the context of potential flow theory. Okay, so the angular velocity of the fluid particle in the flow field is defined by, or is denoted by omega, which is defined as half of the curl of the velocity field. Okay, so I guess there is no need of defining what curl basically means. It is basically cross product of the nebula operator and the velocity field. Okay. Similarly, the vorticity, which is denoted by omega, is defined as by its very definition is actually equal to the curl of the velocity field. Okay, and since you can clearly see now here that the vorticity is actually 2 times the angular velocity of the fluid particle. Okay, so how this is derived, how the rotational elements are then derived, and how then we reach to this final form of the equations is discussed in a very detailed manner in the video lectures. So I would suggest that you go through it so that you get a very proper idea of how these terms are being generated or formed, and how to actually visualize this rotation of the fluid element. Okay, so okay then, now for the case of irrotational flows, like till now we have discussed incompressible flows, steady flows. So if we are considering the flow to be irrotational, for irrotational flows we would have the curl of the velocity field to be equal to 0. Okay, and here like it should be a 0, should be a vector. So I am again sorry that it looked as a scalar, so it should be a vector. Okay, so 0 vector with 0, that each and every component of the curl of the velocity field would be equal to 0. Okay, now this is a very important corollary. Okay, or conclusion. Like for irrotational flows, we would have the curl of the velocity field to be equal to 0. Okay, and this definition is again a very important corollary to the very definition of irrotational flows. Okay, so it states that if a fluid element in an in-viscid flow does not rotate to begin with, it never rotates. So it basically means is that if the flow is initially irrotational, it will always remain irrotational. Like if the flow is irrotational, given that the flow is in-viscid, the flow will always remain irrotational. Why? Because we observed in our previous session there, or in the previous lectures, that the presence of a wall generates or the rotational effects, like the presence of wall is actually the source of all rotational effects in the case of a flow field, right? The wall would generate the rotation in the fluid element, that which in turn generate a rotational flow field, right? But since we are telling that the flow, to begin with, the flow does not have any rotational element, like there is no wall or no outside element that would generate rotational effects in a flow field. So if the flow is devoid of any walls, and if the flow is in-viscid, so there is no source that would generate any rotational effect in the flow field. And that's why it says that if the flow is irrotational from the beginning itself, and the flow is in viscid, then the flow would remain irrotational forever. Okay, so it's a very important corollary. And how this is applicable, I guess it was discussed in the lecture. Like it was told that, like, if we are considering a very wide channel, and wide and deep channel, and if the flow within the center of that channel, okay, within the center of the channel, if we consider, like, it is far away from the walls, right? We can consider that the effect of the wall is not felt in the center region of the channel. And if the flow is irrotational to begin with in that particular channel, then the flow will remain forever irrotational. Okay, so that's a very important corollary. And then, like, if this effect is valid, and if this approximation is imposed, then we can solve the flow field in that particular region by implementing the governing equations for the potential flow theory. Okay, so this is very important. Okay, then again, as I mentioned, that I will not go through each and every definition very thoroughly. I will just go through definition, read the formula, and just then directly apply it to the problems, so for the sake of saving time. Okay, so if you have any doubt, just go to the lectures once again, lecture by Prof. Gupta once again, so that your concept is clear. Okay, so a vortex line is defined as a line which is tangent to the vorticity vector omega is equal to del cross V at every point. Okay, similar to the case of streamlines, where streamlines were tangent to the velocity vector in the flow field, a vortex line is a line that is tangent to the vorticity vector in the flow field. Okay, and similarly, a vortex tube is a bundle of vortex lines passing through a closed circuit C within the flow field. See, here the closed circuit basically means a closed loop in the flow field. So these are the vortex lines, and then this basically represents a vortex tube. Okay, now I'll just go to definitions, and then we'll just apply those definitions and understanding to our problems. Okay, so strength of a vortex tube. Okay, the strength of a vortex tube is defined by the product of the vorticity normal to the surface enclosed by the curve C. Okay, so here the area that we consider is the area enclosed by this closed circuit, okay, or this closed loop in a vortex tube. Okay, so it will basically give the integral of the area, integral over the area, over the area enclosed by curve C, and the product of the vorticity vector omega and the area vector. Okay, where omega is basically del cross V. Now, by applying Stokes theorem, okay, as we know, Stokes theorem connects the surface integral to the line integral. So by implementing Stokes theorem in this equation, we find that if we redefine omega as del cross V, we find that this area integral could be converted to a closed line integral by this relation, right? And then we get that this entity that we get, the closed line integral of the velocity vector in the over a closed line integral over the velocity vector in a closed loop is defined as a circulation. Okay, so you can clearly see there is a, in these two terms, these two integrals, basically this and this are equal, because this is just converted to this by applying the Stokes theorem. Okay, so that's why we see that here the circulation about a circuit is equal to the vortex strength of the vortex tube formed by the vortex lines passing through each point of the circuit. Okay, so it's basically the same. So, but it's a way, it's just a definition to tell that they are equivalent, but these are actually the same thing. Okay, so just the way it is defined, it's a bit different. So you need to just look into it. You need to check. You need to observe it properly. Okay. Now, again, this is again a very important corollary that of the potential flow theory, that is that there is no net component of vorticity to a closed surface. Okay, and this is just comes again by the application of the Gauss divergence theorem. So if you recall, like we have implemented Gauss divergence theorem once before in our understanding. If you recall that we have implemented this in while deriving the differential form of the governing equations from the integral form by applying RTT, right? So there we dealt with the surface term, we converted the surface integral term to volume integral by applying the Gauss divergence theorem, right? Similarly, if we apply Gauss divergence theorem to this integral, we can convert this surface integral to a volume integral by applying Gauss divergence theorem. So this is what we get. Now the integrand that we get, delta dot del cross omega, I'm just saying delta is actually Nebula operator, but I'm just saying delta. So delta dot del cross omega, here, like this is equal to 0. Like for any vector v, like for any arbitrary vector v, this identity or this relation would be equal to 0, and that's why, since the integrand is 0, the integral then would be 0. It basically tells that there is no net vorticity component to a closed surface. Closed surface means a closed surface or closed volume you can consider. So there is no net component of vorticity to that closed surface. So this is actually an outcome of the very inherent nature of the potential flow field, but we are just proving it mathematically by the application of the Gauss divergence theorem. Okay, so by looking to this, we cannot say it is equal to 0, but once we apply the Gauss divergence theorem and we are dealing with this term, we can clearly say that, because since this is 0 for any vector v, then this will be 0 for this as well, and that's why this is also equal to 0. Okay, again there are some corollaries of the flow field, so I will not go through this. These are important, I guess. You can just go through these definitions in the video lecture, that will be better. And also Professor Gupta has very beautifully explained each and every line of this, so I think that will be good. But again, this is very important. You can look this also in the lectures, but I will just go through it once, because this definition itself usually comes in many competitive exams, like what is the Kelvin separation theorem, or what does it state, what is the mathematical formula Kelvin separation theorem. So this usually comes in the competitive exams, so I'll just go through it. The circulation around any material loop in an inviscid and incompressible fluid does not change with time. Okay, so basically means that the complete derivative of the circulation in the flow field will be equal to 0. Okay, so now we go on to derive the governing equations for the potential flow field. Okay, like we already know there's an Euler's equation. We will just see like how to simplify it even further. Okay, so we look into that. So from the Euler's equation, because we know this is the governing equation for the potential flow, from the Euler's equation we get that we get this from the equation. So now if we use this vector identity so that we are able to deal with this term, we apply this vector identity, and again just go through the steps. We see that this would be equal to v dot del v, it's not a dot product, okay, minus half nebula into v square, okay, operated on v square. Then this would be equal to sorry, I have done a big mistake here, that's why I was confused. So I have to write it again. It's actually v dot this is basically again this term, right? So if we substitute this in this term, we get the final form of the equation as this, and this again looks a bit familiar, right? It looks as the Bernoulli's equation term, right? So this is again the beauty of the Bernoulli equation, like how we can deal come with the reach to the same conclusion by different approaches. Here also, if we consider the flow to be steady and irrotational, then this basically becomes constant. Okay, so becomes constant. So now if we take the curl on both sides of the equations, we finally get that complete derivative of the vorticity vector is equal to this. Okay, and here this is like this identity or this definition term is a vorticity transport equation. Okay. So now we come into potential flows. Okay. See, by its very definition, the integral v dot ds, integral of v dot ds, this integral is independent of the path and is a function of location points a and c. Basically, it tells that the integral of v dot ds is a point function, so it will only depend on the n points or the points along which or points between which the integration has been done. Okay, the endpoints or limits of the integration. Okay, the endpoints of the integration. So this would be, this integral would be just basically be equal to the value of the function at point c minus the value of the function at point a, and this is only possible when we can represent the vector, the velocity vector, in the form of a gradient of a scalar. Okay, so v would be equal to gradient of a scalar, say phi, and this phi that we get is actually, this scalar phi that get is actually termed as the potential function. Okay, potential function. Now from the continuity equation we have that, because since we have from the beginning itself we consider the flow to be incompressible, like if we consider the flow to be incompressible, then we get that the continuity equation will take this form. If we are dealing with 2D flows, then it will have only two components, so it will get dou u by dou x plus dou u by dou y is equal to 0. And just for simplification, it's not like the stream function that the potential function is not defined for 3D flows. It is well defined for 3D flows, but just for the context that we are dealing with 2D flows, and so that we can as you'll eventually see, develop a relationship between the stream function and the potential function. That's why we are, just for sake of simplicity, we are dealing with 2D flows for now. Okay, so this is the form of governing equation, right? And now, and the momentum equation, that is basically the Euler's equation for a steady incompressible flow, is given by these equations. Okay, these equations subjected to the boundary conditions at the walls. Since it is only first order non-linear, so this would have one set of boundary conditions that it need to satisfy. Okay. Now, for an inviscid incompressible flow which is irrotational as well, then the continuity equation will take the form of this. Okay. Why? Because if we substitute the value of u and v in this, like since v is given by this, then it will basically mean that u would be equal to, and v would be equal to dou phi by dou y. Why? Because it's very simple again. V is u I cap plus v j cap would be again equal to, since it's enable of gradient of the scalar, it will be equal to dou phi by dou x I cap plus dou phi by dou y j cap. So by the equivalence we get that u is equal to dou phi by dou x and v equal to dou phi by dou y. And if we substitute this relation in this equation, it will basically give us dou square phi by dou x square plus dou square phi by dou y square, it will be equal to 0. Okay, that is what we actually got. This, and which has a very popular form, that del square phi equals 0, and this is a very popular equation in the context of PDEs or understanding of various various physical problems or steady thermal conduction, thermal diffusion. Like, it's a very popular problem. And this equation is termed as the Laplace equation. Okay, then I'll just request you to wait for 2 minutes. I'll just come back in 2 minutes. So hope that you understand. Just wait for 2 minutes. Okay, I'll return. Okay. Again, I'm sorry for the delay from my side. So we can continue now. So we would have a we have a second order. Now we have a second order linear partial differential equation in two dimension, and which will be subjected to these sets of boundary condition in all the ones. Okay, since it is in two dimensions, so we would have four boundary conditions. It is one boundary condition. There is no penetration boundary condition in each and every one. Okay, each and every surface. So this condition has to be satisfied. So now we can see that if we are able to, now this is very important. Okay, that's why I want to emphasize it upon it a lot. Now we can see that if this equation is solved, anyhow, like if we see if this equation is, we can solve this equation, then we do not have to like if we solve this equation, we get the value of phi. Okay, solve, we get phi xy. Phi is a function of xy, and we know that u is equal to dou phi by dou x and v equal to dou phi by dou y. So now we can see that we only used a simple assumption that the flow is irrotational and as well as inviscid and steady state. Inviscid, incompressible and irrotational. Like, and if these three conditions are satisfied, like which can be done like with some certain assumptions, like if we assume that if we consider a flow of water in a channel like the one that we discussed previously, like if you're discussing flow over a channel and we are just solving for a region within the center of the channel where it is devoid of all the viscous effects of the banks or the edges of the channel, then that particular region would be irrotational, inviscid, then this basically that will imply inviscid and as well as incompressible, because the fluid that we use is essentially incompressible. So flow in that region would be governed by this equation only, right? This equation, and if we are able to solve this equation, there is a Laplace equation, we get phi, and if we know phi, then we know the velocity components, right? Now you can see like it's so simplified, it's so simple, right? Now instead of having to deal with a non-linear equation, we can only deal with this beautiful simple linear equation, solve for phi, then it's very, then simply then we can just obtain the velocity fields, and that's the strength or the elegance of the potential function. Okay, like in the case of stream function that we saw, that even if we are defining a stream function simplifies the governing equation, but still we are having, if we are going to similar stream function, like if you are going to still, like if you know the stream function, you know the velocity field, right? You need to solve the governing equation, then find the stream function, and then once you know the stream function, you will be able to find the velocity components, right? But here we do not need to deal with the non-linear equation at all, the non-linear part of the equation at all. But in the stream function, we are having, if we want, like the stream function, if you recall, u is equal to dou psi by dou y, and v is equal to minus dou psi by dou x. And this, if we substitute in the if we substitute in the continuity equation, we just get that this will inherently satisfy the continuity equation. But it does not give any conclusion. Okay, psi is still psi, like we do not know psi, like psi is not solved now, right? It's not solved yet. To solve psi, we again need to substitute psi in the Navier-Stokes equation, which is again non-linear. Okay, it is again non-linear. So we just saw that if we Since we just saw that the stream function is useful in the case that if the flow is 2D and incompressible, right? In that context, psi is valid. So there, if we substitute psi in the our Navier-Stokes equation, we see that our equation is now reduced. Instead of solving for u and v, we just need to solve for psi. There also, like I will just give an example. Like if we need to deal with, say, a in the creeping flow regime, if we try to solve the Navier-Stokes equation, we see that the both sets of our for a 2D flow, both sets of our this x momentum equation and y momentum equation reduces to and steady flows as well, reduces to this equation. Okay, this is again known as the biharmonic operator. But this operator itself is again not linear. Okay, this is okay. I'm sorry. So we deal with this equation, and this has a form given by del 4 psi del x square plus del 4 del x square del y square plus del 4 del y square. Okay, sorry, del y to the power 4. But again, this is the equation that we get, and this again a bit more complicated to solve compared to this set of equations. Okay, compared to this set of equations. So what I'm actually trying to point out in this, like I might have like what to say, diverted a bit from the topic, but what I wanted to emphasize more is that the beauty or the highly relevant nature of the potential flow or the potential function. Like it simplifies the Gaussian equation a lot, right? Since it's decoupled from the Euler's equation, we are not having to deal with Euler's equation at all, right? We do not need to deal with the non-linear equation. So we just need to solve this set of linear equation, get phi, and then get the velocity components. And now once if you know the velocity components, we can just substitute the value of the velocity components in this equation and then find the value of pressure. Okay, so this is the elegance of the potential function, and that's why this theory is like so much relevant in the case of potential flow theory, and also helps us to get an idea of the flow physics in the case of viscous flows as well. Okay, so now if we want to find the slope of this potential slope of the potential lines, like what basically the lines of constant velocity potential are called potential lines. So for 2 dimensions, like if we want to find d phi, the change in phi, so it will be given by, and if phi is a function of x and y, it is given by dou phi by dou x dx plus dou phi by dou y dy, and it will be equal to u dx plus v dy. Since by definition dou phi by dou x is equal to u and dou phi by dou y is equal to v. To find the slope of the, if we just play with this equation and find for the slope of the line of constant potential, that will basically mean d phi equal to 0 will be given by dy by dx is equal to minus u by v. So this represents the slope of the lines of constant potential. Okay, now if we recall from our discussion of stream functions, we saw that the slope of the stream functions are given by this equation, which is dy by dx equal to v by u. Okay, and now if we multiply both these slopes, okay, the slope of the stream function and the potential function, we get that the product of the slope of the potential function and the stream function is equal to minus 1. And if we recall that if the slope of two lines, if the product of the slope of two lines is equal to minus 1, it essentially means that the two lines are perpendicular to each other. So that's why we see here that the potential lines and the stream lines are perpendicular to each other. And now we saw that u is equal to dou phi by dou x and v equal to dou phi by dou y. If we are discussing 2D flows, and similarly again for stream functions, we saw that u is equal to dou psi by dou y and v equal to minus dou psi by dou x. Okay, let's not confuse it. Now we see that since u represents the same velocity component, then it will basically mean that these two are equal and these two are equal, right? And then we get that dou phi by dou x is equal to dou psi by dou y and dou phi by dou y is equal to minus dou psi by dou x. Okay, and that's why for 2D flows, these represent a very important relations known as the Cauchy-Riemann conditions and are very important in the context of potential flow theory because it helps in obtaining the stream one of the other if one is known. I basically mean to say is that if we know the potential function, we can easily determine the stream function from these relations, right? And if we know the stream functions, we can easily determine the potential function. Now, as we saw that the determination of potential function is much more simpler compared to the stream functions, because we saw that for obtaining the stream function, the stream functions are not actually decoupled from the momentum equations. We need to substitute the I'm sorry, we need to substitute the stream function in the momentum equation. Then we get somewhat complicated equation because equation is still non-linear, right? It will remain non-linear, and for some very specific cases only we get a linear equation in psi, which again a very complicated because it's a fourth order equation. We need to again specify relevant boundary conditions for psi and then determine psi. So the determination of psi is actually very difficult in the case of fluid mechanics, but still much more simpler than solving for u and v itself. That's why the importance of psi that's why the definition of stream functions become very important, right? But still, compared to potential functions, again the determination of stream functions are much more difficult, and that's why for a potential flow theory where the flow is irrotational, that one more constraint comes to the flow field, that it is inviscid and 2D, that is inviscid 2D as well as irrotational, and if it's incompressible as well, then our governing equation is very simple. We can just determine phi, and once we know phi, we can determine the stream function from the Cauchy-Riemann conditions. Okay, but it's again only valid for 2D case, because in 3 dimensions, even if the velocity potential exists, stream functions won't come into picture, and then we cannot find a relationship between the stream function and the potential potential functions. Okay, so that's what we will see in our case. Here for most of the flows we will find the potential function because it's much more simpler to find, and then using the CR conditions or the Cauchy-Riemann conditions we determine the stream functions. Okay, and then when both the stream function and potential function is known, we can use either one of them to find the velocity components. Okay, so this is the algorithm that we are going to follow. First, find the potential function. From the potential function, then use either whichever is easy, but in most of the cases finding the potential function is much more simpler. So once you find a potential function phi, then find psi. Then if both are known, then you can easily find the velocity components. Okay, so now we will be dealing with some specific flows, very simple flows, and we'll see how these equations, the knowledge of these simple flows can help us to understand or deal with a bit more complex flows. Okay, like how the idea of some simple flows can help us to understand the flow physics of a bit more complicated flows. Okay, we will look into that. Why this happens, we will again see why it is possible. Okay. So for uniform flow, again, these equations, like some of them are quite simple. It's quite, you can just see and tell this is valid, but some equations may be a bit complicated. So the derivation of the equation may be a bit complicated. So I will suggest that you go into the lectures again, see the definitions, or you can refer any of the standard fluid mechanics books. So there these derivations will be there. Okay, so I will not go to the derivations just for the sake of saving time, because we need to discuss many problems today. Okay, so for uniform flow, here the velocity components are given by u is equal to v naught cos theta and v is equal to v naught sin theta, where v naught is the velocity of the free of the incoming flow. Okay, or a free stream, because there is no viscosity, so there is no point of generating velocity profile, so it will be uniform throughout the flow field. Okay. So phi is given by u ux plus vy, so it is given by v naught x cos theta plus v naught y sin theta. Psi is given by minus v naught x plus uy, this is equal to minus v naught x sin theta plus v naught y cos theta. Okay, just remember the formulas so that we could apply it in our problems. Okay. For source and sink flows, now we again, since again, as I told, since finding phi is very simple, first we start by finding the potential functions. So the Laplace equation in 2D case will govern the flow field for the for this kind of geometry, because we are doing cylindrical coordinate systems. Then for axisymmetric flows, that is the flow is independent of the theta coordinates, this term will be equal to 0. Then we will be only left with this term. Okay, first term, which is a second order equation, and if we solve it, our solution will be of this form. Okay, C1 ln plus C2. And there's a very common practice in setting the arbitrary constant as 0. Like if we consider that as our reference, like if we start like we say that the potential function that we are choosing, if it is set equal to 0, the arbitrary constant for psi is considered to be 0 for the first potential function or the first potential line, then with respect to this we can determine the other potential lines. Okay, so this can be done. So this is a very common practice in setting the arbitrary constant to be equal to 0 in the case of potential flow theory. Okay, and you will see that this is done in many of the cases. So if I in the later slides, if I just set the arbitrary constant to be 0, then just don't get confused. Okay, it's a very standard practice in the case of potential flow theory. Okay, so if we set the arbitrary constant C1 is equal to 0, C2 is equal to 0, we get that phi is equal to C1 ln or C ln. Okay, since we are dealing with only one constant, so we can tell C1 equal to C, so phi is equal to C ln. Okay, now this is the and you will see that this is the fundamental equation solution for a Laplace equation for 2D axisymmetric flows. Okay, so this is the form of all the solutions for a Laplace equation for 2D axisymmetric flows. Okay, now we see that if we have phi, then we can now compute Vr and V theta, because we know the relationship. Then Vr is given by dou phi by dou r, which is equal to C by r, and V theta is equal to 0. So this tells us that the V theta component in the case of source or sink flows is equal to 0. Okay, there is no angular component of the velocity field, so the velocity field is only radial in the case of source or sink flows. Okay, and if the flow is outwards in the case of a source, C would be positive, and if the flow is inwards in the case of a sink, then C would be negative. Okay, as mentioned here, and you can see the potential flow lines, since phi is dependent on r only, so the red lines, these red lines represent the potential lines, and since we know that psi is perpendicular to the potential flow line, these black lines, it is perpendicular to each and every point of contact in the potential lines. With the potential lines, they are perpendicular, and that's why this psi represents the stream function. And if we use the CR conditions to solve for psi, we get that psi will be equal to q theta by 2 pi. Okay, this is the relation for psi, the stream function. Now, if we evaluate the volume flow rate, okay, if we evaluate the volume flow rate through a particular uh, closed circuit. Okay, so if we consider this to be a closed circuit, and if we want to evaluate a volume flow rate outwards to this from this closed circuit, uh, this will be given by VR is it will be given by this integral, where the integral is over 0 to 2 pi VR, there's a radial velocity component over RD theta. Now you may ask a question that since we are dealing with volume flow rate, like, then why the integral is over a line? Okay, why it's a line integral rather than a surface integral? See, this all the game of dimensions. Okay, in the case of 3D flows, okay, in the case of three-dimensional flows, where we have the flow is itself three-dimensional, we see that even if the flow is 1D but the geometry is three-dimensional, for example flow through a pipe, okay, we see that while evaluating the volume flow rate or the mass flow rate, we actually integrate over the surface. We integrate over the surface across which the flow is taking place. Okay, but since the dimension here is itself 2D, so the flow that will take outwards is across actually a line. Okay, this closed circuit, this circular line, and that's why we are to find the volume flow rate, we are considering an integral over this closed circuit, and once we evaluate this, we get that this integral will be equal to 2 pi c, and which we represent it as q, which is termed as the strength or the volume flow rate. Okay, so in many questions or problems, it will be represented as volume flow rate, and its unit will be sometimes meters. Its unit will be meter square per second. So don't get confused. Like, actually, by definition, we know that the unit of volume flow rate is meter cube per second. But why it is written as meter square per second? We need to remember that it's in the case for a 2D flow. Okay, and that's why it is meter square per second. So if it is q is equal to 2 pi c, then we get c is equal to q by 2 pi. Okay, so just wait, I guess someone joined. Okay. Yeah. Okay, that's quite okay, no issues. So since q is equal to 2 pi c, then c is given by q by 2 pi. Okay, and then thus, since we know the value of c now, phi will be given by q by 2 pi ln r. Okay, which is the velocity potential for the source of strand q. Okay, and by applying shear conditions, as I already mentioned previously, psi is equal to q theta by 2 pi. Okay. Similarly, now we look into line vortex or free vortex. Okay, where the governing equation is again dou square phi by dou theta square, because here the radial component of the velocity is 0, so any derivative with respect to towards the radial direction is 0. That's why we only left with this governing equation, and this is a very simple 2D second order PDE. So, and since phi only and that's why this equation will go the solution of this equation is given will be of the form phi equal to c theta. Again, there is an arbitrary constant c1 c2, but we set it to be 0, right, like we did in the previous case. So the solution of phi is equal to c theta, and since phi is now we can determine the velocity components, that is the radial and the angular velocity component. So here, since we are 0 from the beginning itself, so the only velocity component that we need to deal with is the radial velocity component, and v theta is given by 1 by r dou phi by dou theta, which would be equal to v theta is equal to c by r. Okay, so this is the angular velocity component. I think I am making some mistake by naming v theta as angular velocity. So because it may sometimes may get confused with, it is being confused with omega, so I'm sorry. So let me just tell it as v theta. Okay, so v theta is given by c by r. Okay, now if we calculate the circulation about a circular circuit of radius r with this velocity component, then we get the circulation would be equal to the closed integral of this velocity component over a closed circuit in the flow field. Okay, so that will be given by integral of 0 to 2 pi v theta into r d theta. Okay, which will be again be equal to 2 pi c, where c is the arbitrary constant that we chose. So from this we get that c, since gamma is equal to 2 pi c, then c would be equal to gamma by 2 pi. Okay, so from that we get that Vr equal to 0 and v theta will be equal to gamma by 2 pi r. Okay, so phi would be equal to gamma theta by 2 pi. Okay, and from shear conditions again we apply the same algorithm. We first find phi because it's much more simpler to phi obtain. Then from applying shear conditions we find the value of the stream function psi, okay, which is given by minus gamma by 2 pi ln r. Okay, here again we see that since phi is dependent on theta, these blue lines would now represent the potential lines, and these green lines which are a function of r represent the stream functions, okay, or streamlines. See, this drawing and this drawing may seem like just seem the inverse of each other, and if you want you can recall it like that only. Like for the case of source and sinks, the circular lines represent the potential function, and the lines perpendicular to it, or the lines emerging from the origin, represent the stream function. Similarly, just opposite to it, in the case of a line vortex or free vortex, the closed circular lines concentric circles represent the stream function, and the lines perpendicular to it that emerge from the origin represent the potential function. But here you need to just remember that in the context of source or sinks, the constant that we determine c was actually given by q by 2 pi, where q is the volume flow rate. But in the case of a vortex, it is actually the circulation, where c is equal to gamma by 2 pi. This constant value you need to just recall. So sometimes you may get confused. Okay, so don't mix gamma and q in the case of line vortex and source or sinks. Okay, so it is q by 2 pi and here is gamma by 2 pi. Okay, so don't interchange gamma and q. So this will completely change the meaning of the mathematical equation that you are trying to present. Okay, so this is pressure variation. Okay, I'll just read through it, because since we are dealing with irrotational flows, then Bernoulli's equation is applicable between any 2 points in the flow field. So you don't need to consider whether the point lies on the same streamline or not, because since we are from the very beginning itself we are dealing with irrotational flows, so you don't need to consider the points to be on the streamline. The 2 points can lie on any 2 points in the flow field. Okay, so that's there. Okay, now as I initially told that we were dealing with simple flows. Basically we dealt with uniform flow, source and sinks, and line vortex, right, or free vortex. And now and I also told that by knowing some simple flows we will be able to generate some complicated flows as well. Okay, not that complicated, but relatively complicated flows, just by knowing the solution of very simple flows. Okay, we do not need to solve the flow field over the complex geometries, but we'll just use the knowledge of the solution of our simple flows to obtain the flow over a bit more, I will not say very complicated, but a bit more complicated flow geometries. Okay, so in that context, now the superposition of the solution comes into picture. Now we may recall that why this is valid, because see, since we know phi, and from the beginning itself we are using phi to determine our solutions. Why? See, because we are solving this equation. I'll just write the algorithm that will make it much simpler. We are using this we are solving this governing equation, the Laplace equation, we subjected to the respective boundary conditions, obtaining phi. Then if we want, we can determine psi from the CR conditions, and then since we know phi, determine UNV, and if you know UNV, determine the pressure. So this is the algorithm that we are using to solve the flow field, right? Nowhere here we are having to deal with a non-linear equation. So you may ask, in the case of pressure, there is the equation non-linear. Since for the first times or the first iteration that we are going to solve, we know U and V, that's why the equation is not non-linear, because we are just considering the advective terms to be act as source terms in the sense that the only unknown would be the pressure gradient term in that equation. All the terms, the body force term, that is not existent in the case of Euler equation. We are not considering the body force term in this context. We are only dealing with, or we can say the body force term is embedded in the pressure gradient term, and we are only dealing with the advective terms. And since the advective terms are composed of the velocity components, and since we know the velocity components, there is no we do not need to solve the convective part. Okay, the advective part is already known. So the only part that we need to solve is the linear pressure gradient term. Solve it with respect to a known source term that is composed of the velocity components and its gradients, and just solve the equation, right? So that's how we deal with it, and it's not that complicated. So this is the algorithm that we are following. This is very important. This is what we will use throughout our problem solving part. Like we will find phi, determine U and V. From phi we determine psi. Okay, that's the algorithm. It's very simple. So now here, since the Laplace equation and the applicable boundary conditions are linear in phi, the potential flows in complex geometries can be obtained by superposing the potential flow of simpler flows. Okay, potentials of a simpler flow. Since the governing equation is linear, the superposition of the solutions can be implemented to determine the solution for complex geometries. Okay, and again, this is a very important corollary, so I will just read it once and hope that you get an idea of it. And again, if you have any doubt, please go to the lecture. And I guess it is very understandable, but it's important to know. Okay, one of the more important principles used in the process is the fact that flow is always along a streamline with no component across it. This permits us to replace any streamline with a solid wall without affecting the flow in the rest of the region. Okay, see, by the very definition of streamline, we knew that the flow cannot occur across a streamline. Okay, so any of the streamline in this flow field can be considered to be a wall. Okay, like if there is a streamline here in this context, say there is a streamlines of this manner, then we can say that this. Okay, let me just draw it. That will be better. So, if say there are streamlines of this manner in the flow field, and we are saying that, say, now one of these streamline, just see one of the streamlines, if I say I treat it as a wall, then it can be considered as a wall. Why? Because since we know that by the very definition of streamline, there is no flow across the streamline. So any of the streamlines, not only this, if we want to simulate the flow over a curved surface, then this can be the context, right? This can be the scenario. We consider the one of the streamlines or the bottom streamline as a wall, then the upper streamline represents the flow field. And since there is no flow across the streamline, this region within the streamline can be considered to be the object above which we are simulating the flow. Similarly, if you are trying to simulate the flow between a curved channel or curved channel, then these two streamlines can be considered as our walls, and then the streamlines within these two streamlines, two of the within the two streamlines at the edge, the streamlines within the two streamlines at the edge can be considered to govern the flow between these two streamlines, where these two streamlines can be effectively considered as walls. Okay, so this is what actually we are going to do while developing the solution for some complex geometries. Okay, so I hope it was clear. So now in the case of source in uniform stream, where the superposition is between the solution of a source of strength Q and a uniform flow. Okay, and this will actually give us a half Rankine body. Okay, we will see now what a half Rankine body means, but just to give an idea. So superposition of these two flows will give us a half Rankine body. Okay, where again, since phi is then phi would be the superposition of the potential function of the uniform flow and the source of strength Q. Then it will be given by phi will be equal to V naught x plus Q by 2 pi ln r, and psi will be equal to V naught y plus Q by 2 pi theta. Then in the Cartesian coordinates, it is phi will be equal to V naught x plus Q by 2 pi ln square root of x square plus y square, and psi will be equal to V naught y plus Q by 2 pi tan inverse of y by x, where this is again important, where r is equal to x square plus y square and theta is equal to tan inverse of y by x. Okay, just so that we can relate the Cartesian coordinates and the cylindrical coordinates. Okay, because this is in cylindrical coordinates, like if we Cartesian coordinates if you want to say, and this is in cylindrical coordinates. So since we want a solution in one single coordinate system, we need to consider either one of them to get the solution. Okay, so dealing with your comfortable whatever you're comfortable with, you can change the coordinate system, but in most of the cases, like it is much more simpler to deal with the Cartesian coordinate system rather than the cylindrical or the spherical coordinate system. So we are we're usually converting the cylindrical coordinates to Cartesian coordinate system and then solve the required equations, okay, or the required values. Solve for the required values. I'm sorry. So here now you would be given then a velocity component. See, since phi and psi are known, now u would be given by v naught plus q by 2 pi x by x square plus y square, and v will be given by q by 2 pi y by x square plus y square. Now if we want to find a streamline that passes through the stagnation point, that will be this streamline, then okay, before that the half Rankine body that we are going to assume was given by this. Okay, this is the half Rankine body where source is somewhere here, space somewhere here, and this is a uniform flow, and this is the type of flow that would be generated by the superposition of a uniform flow and a stream. Okay, so I guess like if you just try to visualize a bit, like there is something coming out from this region, flow that's coming out of these regions, trying to spread outwards, and there is a flow that is coming from towards the positive y direction. So since this is going outwards, okay, and there is an incoming flow like this, so there would be some interference of this manner that will result in this flow. Okay, and see, as I told previously, that either of these streamline can be considered to be a wall. So we use that streamline that passes through a stagnation point, because beyond the stagnation point there is, since the u component of velocity is 0, so there is no velocity across the streamline, right? So the flow, since this is the stagnation point, so it basically means that if the object was actually there, the flow would be stopped here, like flow velocity would be equal to 0 at this point, then the flow will try to move past this curved surface, right? So having that idea in mind, so we need to find that streamline that passes through this stagnation point. So now, and if we consider that streamline as our surface or curved surface or wall, then it will essentially give us the wall above which, or the surface above which, we need to find or visualize our flow field. Okay. So if we want to find the streamline that passes through a stagnation point, we just need to substitute u equal to 0 and v equal to 0 in our in the value in these equations, and once we do that, we find that v naught is equal to q by 2 pi x by x square plus y square. And now here we see that if we consider this equation, for this left hand side to be 0, y has to be 0, right? And by the symmetry also we can tell that y equal to 0, but a more robust definition would be that for this to be 0, y has to be 0. So if we know that y equal to 0, we just substitute the y equal to 0 in this equation, then solve for x, then we get that x is equal to minus q by 2 pi v naught. Okay. So the coordinates of the stagnation point in this context is given by minus q by 2 pi v naught 0, where q is the strength of the source or the volume flow rate. Okay. Then the equation of streamline, this streamline, that x as the surface above which we want to visualize the flow, is given by this equation. Okay. Then to find the equation of streamline, we need to find the value of psi at the stagnation point, right? So we need to find substitute the value of y and x, or the coordinates of the stagnation point, in this equation. So once we do that, we find that psi would be equal to q by 2. See here, like when we substitute q by this, the value of the stagnation point coordinates in the equation of psi, here we get that psi at a where a will be the stagnation point, psi at a would be given by, this would be equal to 0, then q by 2 pi tan inverse 0 by 2 pi v naught. Okay. So you may say that tan inverse 0 is equal to 0, but here you need to observe that here, since it essentially tells us this is essentially the y coordinate and x coordinate, so we can see that x is negative. So since x is negative, if we look at the quadrants, so let me just draw it. It will be important because it's a very important concept, and one may get confused if we did not know it properly. Okay. So if we consider y and x here, and here you see that 0 represents the y coordinate, and this is numerator represents the y coordinate and denominator represents the x coordinate. So you can clearly see that y equal to 0, but x is negative. So in which of the coordinates is x negative? Then you can clearly see that x is negative in the second quadrant, right? So for the solution of second quadrant, tan inverse 0 would give tan inverse 0 will be equal to pi. Okay, so if we substitute pi here, we get that psi at a is equal to q by 2. So just substitute the value of psi in the equation for streamline, we get the equation of streamline, or the wall above which we want to solve the flow, is given by v naught r sin theta plus q theta by 2 pi is equal to q by 2. Okay. Or in Cartesian coordinate system, we get this would be equal to v naught y plus q by 2 pi tan inverse y by x. Okay. Now there is a second geometry that we are dealing with. This is a source and sink pair. Okay. So I won't go back and forth again to the formulas. Just consider that these are the formulas for the source and sink. So the potential function is given by q by 2 pi ln r1 minus q by 2 pi ln r2. Okay. If I consider source and sink pair, so this is the source and this is sink, because it will have negative for sink, right, moving inwards. So let me zoom out a bit. Then in the Cartesian coordinate system, it is given by this. Okay, how it is given? It's very simple. Just apply the Pythagoras theorem. So at point 1, it would be, if you consider this to be the x coordinate, then this length will be given by x plus a. So it's x plus a, and this is y. So this will be y square. So this r1 will be given by x plus a whole square, square root of x plus a whole square plus y by a whole square. So y square, sorry. So basically is this. Similarly, we can find for the second one. We calculate r2. This is r2 from the sink. So then it will be given by q by 2 pi ln square root of x minus a square plus y square. Okay. So now you will see that if we superimpose a source and sink pair with a uniform flow, it will give us a Rankine oval. Okay. Like previously we just superimposed uniform flow and a source, so that gave us a Rankine half body. So if you want to superimpose a sink also, it will give us a Rankine oval. Okay. So this is a Rankine oval, or you can essentially consider it to a flow and oval surface. Okay. And if we consider okay, it's a Rankine oval. Now we consider the equation in Cartesian coordinate system again. So I'll move a bit fast because we need to solve some problems as well. So phi is given by v naught x plus q by 2 pi. I will not read it. So phi is given by this equation. I hope it is clearly visible. And psi is given by this equation. Again, okay. And these are the respective values in the cylindrical coordinate system. And again, the similar to the previous case, you can find the stagnation point by equating the velocity components to equal to 0. Then find the stagnation point. And here you can see there are two stagnation points. One would be at the minus x-axis, it's a negative value, and this one has a positive value, and that's why the minus plus sign are given. Okay. So now if we consider the case that if the source and sink pair approaching each other, okay, now if we consider that the distance between the source and the sinks, basically if the distance a here, if it tends to 0, it basically means that the source and sink are coincide with each other. Okay. Or but that will again be a different case, but so that we will not consider that a is equal to 0 directly. We will say that source and sink are approaching each other, so we can say that a tends to 0. Okay, this is the approximation that we need to use. Okay, so I'll just write it here. A tends to 0. This is our assumption. Okay, so again phi is given by q by 2 pi ln r1 minus q by 2 pi ln r2. Then r1 and r2 are given by these expressions. It's very simple. Again, this is for a Rankine oval. Okay. Oh no, we are only dealing with since this is the equations, we are only dealing with source and sink pair. Okay, there is no uniform flow, superimposed uniform flow in this flow. Okay, and R1 in the Cartesian cylindrical coordinate system is given by this form. Okay, so the contribution of source would be equal to this. Okay, so we just so basically this expression. Okay, this one. So if we solve or simplify the equation a bit, we will get that the contribution of source is given by this expression. Okay, and the contribution of sink is given by a similar expression, just there is a negative sign here and at the front. Okay, and what we need to do is to get the potential function, just add these two expressions, and so we get this from the equation. And now if we take the assumption that a tends to 0, we get that this is equal to q by a pi r cos theta plus terms of the order a square by r square, where if we tell that a tends to 0, then this term will go to 0. Okay, so phi now scales as, or almost not scales as, but actually almost equal to q by a pi r cos theta. Okay, I already wrote in the limit a tends to 0. So again, now we can then represent phi is equal to k by pi r cos theta, where k is equal to q into a. Okay. Similarly, if we represent k by pi as another constant mu, let me just write it. Then phi can be given by mu by r cos theta, and psi can be given by mu by r sin theta. Okay, so these are in the limit that the source and sinks approach each other. Okay, and similarly you can find the velocity components. This is written in the theta velocity component. Okay, so this is the form of the uh, potential lines and stream lines that we will get. So how it is derived, I guess it's much more explained in much more detailed manner in the lectures. So I suggest that you go to the lectures for your reference. Okay, so now we'll dealing with some problems. So I hope it was quite clear, like why potential function is useful, and how by knowing the potential function we can determine a stream function and then the velocity components. Okay, we can determine the velocity components from the potential function as well, but see, the beauty is in their coexistence rather than their individual existence. Okay, see, what I'm trying to say is that to properly understand the flow field, irrotational, let me just write it, a irrotational incompressible, say 2D incompressible and inviscid flow, the beauty is in the coexistence of both phi and psi rather than phi and psi individually, because both of them will exist. Okay, so the beauty is that phi is easy to determine. Okay, and psi is easy to visualize. Because we discussed very extensively while we were discussing the flow kinematics part, that how the streamlines help in visualizing the flow. First of all, the streamline is, by its very definition, is an imaginary line that is tangent to the velocity vector at each and every point in the flow field. So by that context itself, it helps us in realizing the direction of the flow field. And again, for steady flow case, the streamlines, the streak lines and the path lines are same. So if the flow is steady, then streamlines itself help in determining the direction of the flow field, because it is equivalent to the path line or the streak line. And also we again learned that the density of the streamline also helps us in determining the magnitude of the velocity. We saw that if the streamlines are very dense in a particular region, we can tell that the velocity is high in those regions, and if the streamlines are far apart, not that dense, you can tell that the velocity is low at those regions. So the beauty of streamlines is in the visualization. Yes, obviously it helps in reducing the governing equation in a single variable, and so helps us in obtaining the solution for a 2D incompressible flow field. But the very manner in which we need to find a solution is a bit more complicated compared to the potential flow. But the beauty is in its visualization. Once we know the streamline, it's very easy to visualize the flow. Okay, once we know the functional form of the streamline, u and v are known. Moreover, since psi is known, we can get a very good idea of how the flow would actually behave in the case of once the streamline is known. But in the case of potential flow or the potential functions, the beauty is in its derivation. Like, it's very easy to determine the potential function. Like, once you know that the flow is irrotational and inviscid as well as incompressible, just substitute the relation u is equal to dou phi by dou x and v equal to dou phi by dou y in the continuity equation. Just solve the Laplace equation subjected to the necessary boundary conditions. You get phi. No need to deal with non-linear momentum equations, right? And once phi is known, since it is easily determined, once the solution of phi is known, just use the CR conditions for 2D flows. Obviously, for 2D flows, just use the CR conditions to determine the stream functions. And once stream functions are known, you just have a very good idea, good knowledge of how the flow is behaving in that particular case. Okay, so this is the the beauty of the potential flow theory. Like, it's very easy to visualize since the potential function is known. Once and just for 2D case, you can easily determine stream function, and just then everything is right in front of you, no complications. Okay, so I hope now you get a very good motivational idea, or the very understanding of why knowing the potential flow theory is very important in the context of fluid mechanics. Okay, so now we solve some problems. So okay, this is a very simple question again. Given u is equal to 2xy and v is equal to a square plus x square minus y square, show that the velocity potential exists and find phi. Okay, see, for the velocity potential to exist, the first and foremost criteria is that the flow should be irrotational. Okay, this is the most important criteria. For the stream function, the flow should be incompressible. Okay, these are the 2D and incompressible. So these are the conditions that you need to impose to justify the existence of the potential function and the stream function respectively. For the potential function to exist, del cross v should be equal to 0, and for the stream function to exist, del dot v should be equal to 0, and the flow should be 2-dimensional. Okay, so these are the things you need to impose to find the stream functions. Okay, so to find the stream function and the potential functions. So once you know that, since for the velocity potential to exist, del cross v is equal to 0. So again, sorry, should be vector. So just find the curl of the velocity field. So once you do that, you find that del cross v is actually equal to 0. So we can tell that the flow is irrotational. So now they are asking that from the given velocity components, determine phi. Okay. So we know that dou phi by dou x will be equal to u, that is equal to 2xy, and dou phi by dou y will be equal to y, that is a square plus x square minus y square. So once you do that, just integrate phi with respect to x, we can get phi is equal to x square y plus some function of y and some constant. We just again set it arbitrarily equal to 0. And then again for the u component of velocity, y component of, sorry, for the y component of velocity, dou phi by dou y will be equal to a square plus x square minus y square. So just integrate it with respect to y, then we get that phi equal to a square y plus x square y minus y cube by 3 plus some function of x. Now we need to compare both these functional forms of phi. Okay, so comparing both of them, we get that phi would be equal to a square y plus x square y minus y cube by 3 plus c. See, this is the trick. This is telling that x square y would be there plus some functional form of y. So we can, in here you can see whether this is exists or not. If this term does not exist here, then there is something wrong in your calculation. Okay, so this term must exist there, must exist here. Plus they are saying that there is some function of y, only function of y. So what are the only functions of y here? That is a square y and a square y and y cube by 3. And again, if you look into here, it said that these are there. This term should be there. Plus there is some function of x. So go back here and see if there is an explicit function of x or any function that includes x in it. So you can see that there is a function of x here, right? Since there is a function of x here, then this should be an unknown function fx here, and since there is y in these terms, y in these terms, and this is similar to this one. So these are the terms that would be the function of y that we need to determine. So this is how the comparison is done. Okay, just compare the two terms and see whatever is missing and whatever is there, then just find the composite form. Okay, so from that we get that phi is equal to a square y plus x square y minus y cube by 3 plus c. Again, if we set c equal to 0, there is a general practice that we told, phi will be given by a square y plus x square y minus y cube by 3. Okay, so this is the functional form of phi. Now again, the question is, for the flow is an incompressible flow defined by u equal to 2 and v equal to 8x. Does the stream function exist? And if so, find the expression. And again, since again I told, to see if the stream function exists or not, first we will see whether the flow is 2D. Since the flow is 2D, first condition is satisfied. The first condition is satisfied. Second condition is del dot v should be equal to 0. Okay, so we need to impose that. So we impose the continuity equation or del dot v. Then we see that dou by dou x of 2 would be equal to 0 and dou by dou y of 8x would be equal to 0. Since del dot v equal to 0 is also satisfied, then we can tell that the stream function exists, and they are asking that then if it exists, find the expression for the stream function. Again, we follow the same algorithm or same steps that we used for potential function. We know that the x component of the velocity will be given by dou psi by dou y. So dou psi by dou y is equal to 2, and we know that the y component of the velocity will be given by minus of dou psi by dou x. So dou psi by dou x is equal to minus 8x. just again integrate it, the first expression with respect to y, we get that psi equal to 2y plus some function of x and some c. Again, for the second component part, again we integrate psi with respect to x, we get that again we integrate a test with respect to x, we get that psi equal to minus 4x square plus f of y plus c. Again we just compare these two terms to get that psi of xy is equal to minus 4x square plus 2y plus c. Set the arbitrary constant equal to 0 to get that psi is equal to minus 4x square plus 2y. Okay. So now we look into the next expression. Again this is similar, but now we are dealing with the cylindrical coordinate system. So the radial velocity of the flow is described by Vr is equal to k by root r cos theta, and v theta, if v theta is equal to 0 and theta is equal to 0, find out v theta and the stream function for the flow. Okay. So here again, since the other component of velocity is not, it's not 0 throughout the flow, but it's told that it is 0 at a particular point where theta is equal to 0. So we need to find a stream function or a potential function, whatever you want you can find, but here we use we find v theta by using the stream function. Okay. So we know that Vr will be equal to 1 by r dou psi by dou theta. So we just substitute Vr value of Vr in this equation to get that dou psi by dou theta is equal to k into root r cos theta. Again we integrate this equation with respect to theta to get that psi is equal to k root r sin theta plus f of r plus some function of r. Again we know that v theta is equal to minus dou psi by dou r. Okay. So we differentiate this equation with respect to r to get that v theta will be equal to k by 2 root r sin theta plus derivative of r. Okay, derivative function with respect to r. Since we know that v theta is equal to 0, v theta is equal to 0 and theta is equal to 0, it gives us that f dash r is equal to a constant. Okay, so we get that v theta is equal to k by 2 root r sin theta. We just set the arbitrary constant c equal to 0 and get psi equal to, and psi we already found out, psi we got as k by root r sin theta, k into root r sin theta. Okay, so this is what we are asked to find. So v theta is equal to k by 2 root r sin theta. Okay. Okay. So just wait a minute. Okay. So this is the equation again. Let's go through it. The wind velocity at a location 5 km away from the center of a tornado, considered to be in viscid irrotational vortex motion, was measured as 30 km per hour, and the barometric pressure was 750 mm of mercury. Calculate the wind velocity 1 km from the tornado center and its barometric pressure. Okay. So I guess it's very simple. So since it is tornado, we are asked to treat the entire tornado as irrotational and vortex, irrotational, in viscid and vortex motion. So we need to deal with the equation for free vortex. But as you might recall that we solved the, we actually dealt with the question which modeled tornado as a superposition of a free vortex and a forced vortex. Okay, so in reality a tornado is modeled by superposing the inner region by a forced vortex and the outer region as a free vortex. So that is actually being done, but here it is told that we need to consider to be the tornado to be in viscid and in rotational throughout its radius or throughout its radius. So we can consider the entire tornado to be in viscid, irrotational, in viscid and irrotational vortex motion. Okay, so there is one important point to know, so that's why I mentioned. Okay, so all the parameters are given. So the velocity at a distance 5 km away from the tornado is given, and the pressure at that point is also given. So since both of these terms are known, we can just apply the Bernoulli's equation to determine the pressure and velocity at other point. Okay, at a different location, which is asked to be at a distance of 1 kilometer away from the tornado center. So why we can apply Bernoulli's equation at any 2 points? Because the flow is irrotational throughout the flow field. Okay. So now pressure so the pressure at point A. So consider this diagram that point A lies at a radial distance of 5 km from the center of the tornado, and point B lies at a radial distance of 1 km away from the center of the tornado. Okay. So pressure at point A is given by 750 millimeter of mercury. So Pa is equal to rho GH, which gives pressure at point A to be 100, almost 100 km per meter square. Okay. Then from a free vortex we get that V theta is equal to C by R. So V theta would be equal to so C would be equal to R V theta. So since C is a constant, we can write that R A V theta A would be equal to R B V theta B, because C is a constant. So essentially it tells that R V theta at any radius at any point, and V theta at that particular radial point should be a constant throughout a tornado. Okay, so it tells that R A V theta A would be equal to R B V theta B. Since R A is known, V theta A is known, and R B is known, we can determine V theta B. Okay. Why I have taken V is equal to why I have taken V is equal to V theta? Because the radial component in the case of a free vortex is 0, right? That's why V would be equal to V theta itself. Okay. So that's why V theta B is given by this expression. Substitute the value of V theta A, RA and RB to get that V theta B is equal to 41.67 meter per second. Okay. So now once V theta B is known, it's very simple. Just apply Bernoulli's equation, because there is only one unknown left. It is pressure at point B. So apply Bernoulli's equation. Then substitute the value of PA, V theta B in this equation to find that PB is equal to 99,062 Newton per meter square. Okay, or 99 kilonewton per meter square. Okay. Now the next question tells that a two-dimensional source of volume flow rate lambda is equal to 22.5 meters square per second. See, this is what I was trying to tell you previously. Like, since the flow is itself 2D, the volume flow rate cannot be in meter cube per second, because there is no context or no concept of a three-dimensional entity in a two-dimensional problem. So the volume flow in that case, even if the term volume is there, but the volume flow, it has a unit of meter square per second rather than meter cube per second. Okay, so don't get confused, because in the context of a source or sink, the source strength is actually the volume flow rate from the source. Okay, so that's one need to remember. So it is given that the volume flow rate lambda is equal to 2.5 meters square per second. Is located in a uniform flow of 2 meter per second. So it tells that it's actually the solution that you're going to get is actually superposition of a uniform flow and the source. It is basically a half Rankine body, right? Determine the stagnation point and the maximum thickness of the resulting half body. Okay, so the question is that I'll just draw a rough diagram. So what is asking us that the solution is now superposition of a source and uniform flow. Okay, so it will generate a half Rankine body. Okay, let's just consider it like this. Now we need to find a stagnation point. First thing is that we need to find a stagnation point. Okay, we'll just use a similar steps that we used while discussing the half Rankine body. Now also we are asked to find the maximum thickness of the resulting half body. So the maximum thickness would be this length. Okay, sorry, this length. So we need to find this length. Okay, that will be the maximum thickness. So first we start with finding the stagnation point. So for a half Rankine body, the streamline of this surface, okay, or wall, is given by psi is equal to u naught. I'm sorry. Just for streamline above this half Rankine body, the equation of streamline is given by psi is equal to u naught by plus sorry, u naught y plus lambda by 2 pi tan inverse y by x. Okay, if we consider this factor lambda by 2 pi is some constant k, then we get that psi is equal to u naught y plus k tan inverse y by x. Okay, so the velocity components are given by it's again very simple, just take the derivative dou psi by dou y minus dou psi by dou x. So u is given by u naught plus k by x square plus x by x square plus y square, and v is given by k into y by x square by x square by y square. So again we use the similar steps to find a stagnation point. Equate u and v to be equal to 0, then find the value of x and y coordinates. So if v equal to 0, again we see that y would be equal to 0. So if we substitute y equal to 0 in this expression, we get that x is equal to minus lambda by 2 pi u naught. Okay, and so x would be equal to minus 2.5 by 2 into 3.1416, that is pi into 2, where u naught is 2. So we get that x is equal to almost minus 0.2 meter. So the stagnation point is at the location of x equal to minus 0.2 and y equal to 0. Okay, so now what we need to do is, since the stagnation point is known, we need to find the equation of the streamline passing through the stagnation point. That will actually be the wall or the surface above which the surface of the surface of the Rankine body. Okay, half Rankine body. So to find the equation of a streamline, we will find the equation of the value of the stream function at the stagnation point. Okay, so psi at minus 0.2 and 0 is given by this expression. So it is equal to 1.25 meters square per second. Okay, then we just substitute this value in the equation of streamline. So we get that u naught y plus lambda theta by 2 pi is equal to lambda by 2. Okay, now we are just dealing with the cylindrical coordinate system. So u naught y would be equal to lambda by 2 minus 1 by theta by pi. Just take this term in the right hand side. So y equal to lambda by 2 u naught 1 minus theta by pi. Okay, so here where y represents this distance, okay, from the x coordinate. So this distance is equal to y. So for y to be maximum, theta should be equal to 0, right? If this term equal to 0, then y would be equal to y max. Okay, so if we look into that, then we see that if we equate theta is equal to 0, then y max is given by lambda by 2 u naught, and the maximum would with this length would will be directly equal to 2 into y max, right? Because just double this length would be, just double this length will give us the maximum thickness, right? So w max will be equal to 2 into y max, so it gives us that w max equal to lambda by u naught, where lambda is 2.5, so we get that w max equal to 1.25 meter. Okay, there is another way to find it out. So if we just use this expression here, and since if the Rankine body, like it by theoretical meaning, it goes on increasing, right? It's not straight like this. So by definition, the Rankine half body thickness goes on increasing as x increases. Okay, so the maximum thickness would be at the point where x tends to infinity, right? X tends to infinity. So if we substitute it here, so it will give us tan inverse infinity would give us to be pi by 2. So we'll get u naught y plus lambda by 2. So we will just get just try it, u naught y plus lambda by 2, and it is pi by 2, lambda by 2. Okay, so 2 pi and it is pi by 2, lambda by 2. So and y will be equal to y max, right? So this can get cancelled. So u naught y max will be equal to lambda by 4. Oh, sorry. So, this was, if you recall, this was, if this tends to 0, then inverse will give us, this will be actually equal to pi. Okay, so if we do that, we get that u naught y max equal to lambda by 2. So, oh, I'm sorry, I'm just getting confused with the calculations. Okay, sorry. So for if x tends to infinity, I'll just write it now. If x tends to infinity, this would give us u naught y max plus lambda by 2 pi tan inverse 0. Since tan inverse 0, it is in a positive x direction, so this will be equal to 0. So y max would be equal to lambda by 2 u naught. Okay, similar result. Okay, now we look at the next question. So it tells that a line source discharging flow at 0.6 meter square second per unit length is located at -10, and sink of volume flow rate 1.2 meter square per second is located at 20. Okay, a line source and a sink. For dynamic pressure of 10 Newton per meter square at the origin, determine the velocity and the dynamic pressure at point 1 and 1. Okay, so it tells us that so this equation is again a superposition of a source and a sink, so it will give a it's just a superposition of source and sink, since there is no uniform flow, so an inclined overbody does not come into picture, so it's just a superposition of source and sink. So we need to find phi, then obtain the velocity components, and then determine the dynamic pressures, because dynamic pressure is given by P is equal to half rho v square by our discussion in the fluid statics part, fluid dynamics part, right? We know dynamic pressure is boundaries equation, so dynamic pressure is given by half rho v square. And it's told that at the origin the dynamic pressure is equal to 10 Newton per meter square. So but here rho is not given. Okay, so first you need to determine rho from this dynamic pressure, and then once rho is known, just substitute, obtain the value at point obtain the value of velocity at point 1 and 1, then find the value of dynamic pressure at point 1 and 1. Okay, it's, I guess the algorithm is known how to approach the problem. Since it is a proportion of source and sink, psi can be expressed as this. Psi is equal to lambda 1 by 2 pi theta 1 minus lambda 2 by 2 pi theta 2. Okay, then in the Cartesian coordinate form, because it's all the distances are, or the coordinates are given in terms of Cartesian coordinate system, so it's better if we deal with that. So we need to convert this expression in Cartesian coordinates, right? So, and if you substitute the value of the strength, source strength, sink strength, and represent theta in terms of the Cartesian coordinate system, we get that psi is equal to 0.6 by 2 pi tan inverse y by x plus 1 and 1.2 by 2 pi tan inverse y by x minus 2. Okay, to obtain the velocity components, we find a derivative dou psi by dou y and minus dou psi by dou x, to get that u is equal to this expression and v is equal to this. Okay, now at the origin x and y both are 0, so we get that u is equal to substitute x and y equal to 0 in this expression to get that u is equal to 0.1909 meter per second and v equal to 0. Why? Because since both are numerators we have y, so since both of them are 0, so we get v equal to 0. So the dynamic pressure is then evaluated as P is equal to half rho v square, but at the origin P is given but rho we do not know, so we need to get rho from this expression. So we get that rho is equal to 2 into P by v square. So since pressure is equal to 10 Newton per meter square at the origin, so the density is given by substitute the value of V as 0.1909, then we get the value of rho as 548.8 kg per meter cube. Okay. Now since rho is known, just repeat the same calculation for the point 1 and 1 to get the value to get the value of U and V, where we once we substitute the value of 1 and 1 at these expressions, we get that U is equal to 0.1335 meter per second and V is equal to minus 0.0764 meter per second. But now, since here V is actually the net resultant velocity, so we need to find the resultant velocity since we have U and V. So the resultant velocity is given by square root of U square plus V square, where VR will be VR is not a radial velocity component. Okay, it's a resultant velocity component. So the resultant velocity component is given by 0.153 meter per second. Then, since we need to find the dynamic pressure, just substitute the value of V in this expression, and rho is already known now. So we get dynamic pressure at point 1 and 1 is equal to half into 548.8 into 0.153 whole square. So we get that dynamic pressure at point 1 and 1 is equal to 6.49 Newton per meter square. Okay, so there's one more question, it's again not that complicated, so I hope we can deal with this. Okay, a source with volume flow rate 0.2 meter square per second. See, in all the questions volume flow is given as 0.2 meter square per second, but not meter cube per second. Why? I guess I already explained many times, so I hope it is clear now. Okay, and a vortex with strength 1 meter square per second. Since see here, for vortex it is not told that it is the volume flow rate but the strength. Okay, so that's why source and sinks are different, source and vortex are different in that picture. Okay, and though the units are same, and vortex of strength 1 meter square per second are located at the origin. Okay, determine the equations of the velocity potential and the stream function phi and psi, and what should be the resultant velocity at the point x equals 0.9 meter and y equals 0.8 meter. Okay, I guess again it's very quite straightforward. We need to find the velocity, we need to find the expression of phi and psi, determine the origin. Okay, so it tells us that x and y are 0. So then determine the equation of velocity. We need to determine the equation of velocity potential and then find the u and v velocity components from the velocity potential or the stream function at these points. Okay, quite straightforward, nothing complicated at all. Okay, so for the source we have psi is equal to k1 theta and phi is equal to k1 ln r, and for the vortex we have psi is equal to minus k2 ln r and phi equal to k2 by k2 theta. Okay, this you will check. We get that for vortex psi is some minus lambda by 2 pi into ln r. So this was there was some minus term. Okay, so we combine this for a stream function for this combination for a source and a vortex. We get psi is equal to 0.22 pi theta minus 1 by 2 pi ln r. Okay, here, and for a potential function we get that phi is equal to 0.2 by 2 pi ln r and plus 1 by 2 pi theta. Okay, why? Because the value of the strengths are already given. Okay, 0.2 and 1, just substitute that. So we get that psi and phi are given by this expression. Then we need to find a velocity component. So VR is given by dou phi by dou r. So just use this expression. So dou phi by dou r, it will give us VR is equal to 1 by 10 2 pi r. Okay, 1 by 10 pi r, and V theta is given by again 1 by r dou phi by dou theta. You can use this expression itself. You can use either one of them, but phi is simple. I used phi here. So V theta is 1 by r dou phi by dou theta. So V theta is equal to 1 by 2 pi r. Just substitute the value of x and y, because it is in terms of r now. You could have directly substituted x and y in this expression also, but simpler here. So we can just substitute the value of r, where we can represent r in terms of the we can represent r in terms of the Cartesian coordinate system. So r would be equal to 0.9 square and 8 square. Why? Because since it is told that because they are told that the vortex and the source are located at the origin, so the radial distance is can be directly obtained by knowing their coordinates. So r will be equal to 0.9 square plus 0.8 square will give us r is equal to 1.204. Just substitute the value of r here. So we get that Vr is equal to 0.026 meter per second and meter is equal to 0.132 meter per second. And since we are asked to find resultant velocity, so resultant velocity will be equal to square root of Vr square plus V theta square, which will give us V resultant is equal to 0.134 meter per second. Okay. So I hope this is all for this week. Again, I hope I might have moved fast a bit in the some of the concepts. It might not be clear at that much, but I hope that the very goal of this session was to implement the concept that you have learned in the lectures. So I hope I have from my side I have extensively discussed the formulas, what they mean, what the terms in the expression mean. So I hope it was clear, and how the velocity fields are obtained once phi and psi are known. So that we have discussed, and we have solved enough problems to get an idea of how to implement those problems, implement those concepts in different problems. Okay, so I hope it was clear. But again, there might be some doubts, so I suggest that if there are any doubts, you can please go back to the lectures, see the lectures by Professor Gupta. I'm 100% sure you will get your doubts clear. And moreover, there's again one problem solving session tomorrow, Monday at 6 to 8 p.m. I suggest that you join that session also. So if there are any doubt, then they can be cleared by the next the other TA also. Okay, so thank you then. That's all from my side for